Okay, so we're picking back up with the slide wire generator, and we're going to do this example together. What it really is kind of like leading you on a derivation of an important equation. Okay, a very simple one, but very important. So if, the things that I do in this example aren't really making too much sense, I don't want you to worry too much about it. Focus on the final result, okay? So let's talk about the setup here. We have a U-shaped conductor in a field that's pointing into the page. Okay, this U-shaped conductor is not a complete circuit until we put this bar on top. So with the bar on top of this U-shaped conductor, if there is going to be a current induced in that circuit, it'll be able to flow completely. And the way we're going to induce a current in this circuit is by changing an aspect of the flux, namely the area. And the way that we change the area with time is we pull this bar to the right at speed v, okay? So we're starting off with this conductor, U-shaped conductor in a field, moving the bar to the right. The length of this bar, which is very important, okay, is L. That's the height. I know it's L. I know it's a height, okay? But it's the length of the conductor that is perpendicular to the direction of motion, okay? And this is a slide wire generator. So let's see how it's going to generate an EMF, okay? And we just said before, it's going to generate an EMF by changing the area with respect to time. So the EMF is going to be, right, d phi b dt. We'll pull out the elements of the flux that are not changing with time, namely b and cosine theta. And what we're left with is dA dt. And so what's theta? Theta is the angle between the b vector and the area vector. And you can see in this example that the b vector is pointing into the page and the area is also pointing into the page. So theta is 0 and cosine is 1. So in order to find the EMF in terms of the variables that we're given, such as L and B and velocity V, we need to find a way to describe how the area is changing with time. So the area right now is, before we start moving the bar, if this is width W, okay, the area of the loop would be L times W, right? So the area, after we start moving the bar to the right, well, it's going to increase in its width, right? So let's call A prime the area after moving the bar. And it's going to be length, which, is the height of the bar, times the new width of the bar. The new width of, not the bar, of the circuit, right? The new width is going to be W plus, well, let me write that better. W is here, right? Plus this piece right here. So what is the width of this piece? Well, the only information we have is that the velocity is to the right. And velocity, you may recall from Physics 1, hopefully you recall this, is, in terms of the variables of this problem, is going to be the change in the width with respect to time, okay? And so if we just want to find out what that change in width is, well, we just move our time upstairs, right, solving for width, and we can see that the change in the width is going to be the velocity times the time it took to move it to that new position. And that's what you see here in this picture, right? This is the little piece of width that has increased since moving the bar to the right. And so then our new area, well, it's going to be, the new width is going to be W plus V dt. And then from this, since we have the area at two different points in time, we can write dA dt as delta A delta t, where delta is final minus initial. So that would be the final area minus the initial area over the time it took to change the area. So all this is going to turn into dA dt, and I'm going to plug it back into epsilon over here on the left. So let's do A prime minus A. So A prime minus A is going to be L times W plus V dt minus LW. Well, that gets rid of, if I, distribute everything, the LWs go away. And what I see is that the change in area is equal to LV dt. So that's A prime minus A. Well, let's plug that into dA dt, right? So then dA dt, the numerator is going to be LV dt, the denominator is dt, and now those dt's are going to go away. And what I see is that the change in area with respect to time, is simply equal to LV. So I plug that guy into my EMF up here, and I see that my EMF is negative B LV. Okay, so this is the important result, the important equation. So the EMF, so the voltage that is generated in this situation of the slide wire generator, is minus BLV, where B is the field, L is the height of the circuit, right? And more specifically, it's the size of the circuit that's perpendicular to the direction of motion, okay, times the speed of the motion to the right. All right, so that's kind of a fun derivation, and so the result is, right, the EMF generated is minus BLV, and if you wanted to find the current, well, current is simply voltage over resistance. So if we knew the resistance, it would be, the current flowing would be minus BLV over whatever the resistance is, okay? So we can skip this this example. It's just kind of, it's adding in some physics 1 content. So it's not really, you don't really need to do this at all, okay? I'm not going to be testing on anything like this. Okay, but I do want to do some conceptual stuff with you guys. And this is one of them, okay? So we have a wire coil that's being squeezed, okay? And it's in the presence of a magnetic field pointing into the page. So the question is, while the coil is being squeezed, is the induced EMF in the coil clockwise, counterclockwise, or zero? So while something is being squeezed, okay, that's the key word. If something is being squeezed, its area is decreasing, right? So while squeezing occurs, our change in flux will be negative, okay? Because dA dt will be less than 0, right? It's being squeezed. We're changing the area with respect to time. We're shrinking the area with respect to time. So Lenz's law tells you that the direction of the induced EMF that's generated by changing the flux, that direction is related to an induced magnetic field that opposes this flux, okay? So we're going to do the right-hand rule on the magnetic field. So right-hand rule on B induced, the induced magnetic field. B induced opposes the change in flux. So our flux is decreasing, okay? So if our flux is decreasing, the induced magnetic field is going to point in the direction to oppose the decrease. And the way we oppose decreasing vectors, right? So if B is pointing into the page, right? B is pointing into the page. The way we oppose that vector getting smaller is by adding another one in the same direction, right? So our B induced here is going to also be into the page. Okay, technically it'll be up here, but I was just drawing it down there up for no particular reason. Okay, so our B induced is up here, technically. And so we're going to do right hand rule on B induced. So our thumb will be into the page and our fingers will be curling in the clockwise direction. So clockwise is the answer for part A. Part B, once the coil has reached its final shape. So what does that mean? When it's reached its final shape, the shape is no longer changing, right? Once you arrive at your destination, you are no longer traveling. Okay, so once you reach your final shape, you are no longer changing shape. So that means your change in flux will be 0 because dAdt is not changing anymore, right? There is no dAdt. So if there's no change in flux, then there is no EMF. All right? No EMF and thus no current. So 0. And by the way, I don't know if I mentioned it last. I might have mentioned the last lecture, but epsilon and induced current are in the same direction. Okay. So that's a really good understanding. So let's talk about Lenz's law. All right. Lenz's law goes along with Faraday's law. It's basically, right, if this is Faraday's law, Lenz's law is basically giving you the direction of this minus. Okay? Through numbers alone and on a circle, it's very difficult to decide, like, what's the minus, what's the negative direction. The negative direction is this. Okay? It's opposing the cause of the induction effect. Okay? So, it's opposing the cause of the change in flux. That is going to be the direction of the induced EMF. And so, well, the induced EMF, how is it there? It's created by an induced magnetic field. And so that induced magnetic field that's attached to the EMF, right? These belong together. These are related to each other through the right-hand rule. So if you know this, you can figure out this. If you know this, you can figure out this. Okay, they are attached together. And the rule that decides the direction of B induced, well, it's whatever direction opposes the change in flux. Okay, and that change in flux can occur through a changing B field, through a changing area, or through a changing angle. Okay, so let's go over some examples for that. So let's just talk about this example. And it's exactly the same as the one we did, except we're going to figure out what the direction of the current is. Okay, so let's see if we can figure it out without looking at the picture. So figure it on our own and then compare it with the picture. So the change in flux that was occurring in this slide wire generator was what? The area was increasing, right? The area was increasing, therefore the flux change was also positive. And the direction of the induced current will be related to the induced magnetic field, which opposes the change in flux. What direction should B induced point in order to oppose an increasing flux? Well, B induced should point in the opposite direction to the magnetic field, okay? Because we want to stop the increase. So if this B field vector is increasing into the page, technically, actually, you know what's increasing into the page? The area vector, right? If we're increasing area with respect to time, the magnitude of that area vector is going to be getting bigger, okay? And so what we need is to oppose that. Well, we can't go and make it smaller. What we need to do is impose a magnetic field opposite to this one. Okay, so pointing in the opposite direction to B. That's going to be our direction of B induced, because we want to oppose the change in flux. So we want to make that flux no longer increasing. We want to stop it from doing that. So we apply a B field out of the page, and then with your thumb pointing out of the page, you curl your fingers naturally with your right hand, and they occur in the counterclockwise direction, which is what we have here, right? And E and B are in the same, E and I are in the same direction. Okay, that's B induced out of the page. Okay, so that's how you tackle this problem and similar ones in your homework where you see an area changing with time. Okay, so let's look at this example. Let's do the same thing. We have a loop. We have a B field pointing up, and that B field is increasing with time. Okay, it's increasing with time. So what direction should B induced be to oppose the increase? It should point in the opposite direction of B. B induced is pointing down. We put our thumb in the direction of B induced, and the directions that our fingers curl is clockwise. So the induced current and the induced EMF will be clockwise. Okay, so that's the direction of the resulting induced current. And that's basically applying Lenz's law. So let's look at some more scenarios. So now the magnetic field, let's erase the answers. Now the magnetic field is being created by a magnet instead of just a vector, okay? So, and the way we're changing the magnetic field is we're bringing the magnet towards or away from the coil. And if the magnet has the North Pole facing down, we recall that the magnetic field vectors that leave the North Pole, right? So that would be a downward facing magnetic field vector coming from the magnet. If we're bringing it closer to the coil, the strength of the field is going to increase. Okay, right? It's going to be getting bigger. So I guess what I should say is dV/dt is getting bigger, right? In the downward direction. And so now we need to figure out, okay, if the flux is increasing, right? If dB/dt is increasing, that means the flux is increasing. And the direction of the induced current will be such that the field it creates opposes that change. So let's find the direction of the induced field that opposes this increasing flux. Well, to oppose a downward magnetic field that's getting bigger, we need to apply an induced field pointing up. Okay, so that's going to be the direction of the induced field that creates the induced current. So with our thumb pointing up, we see that our fingers will be curling in the counterclockwise direction. And so the induced current will be counterclockwise. So what about, before we do this case, okay, because we're flipping two things. You see, we're flipping the the direction of the velocity and the magnet. Let's look at the velocity going up with the North Pole pointing down. Okay. So here we go. The North Pole is pointing down. Our B field is pointing down still, right? But we're pulling the magnet away. If we're pulling the magnet away, then the magnitude of B is going to be decreasing. The flux will be decreasing. And so the direction of the induced field will need to point in the same direction as B in order to oppose the decrease. So with our thumb pointing down now, our fingers are going to curl in the clockwise direction. Let's go back to this case up here. So let's point the South Pole down and bring the magnet away. Okay, well, automatically we know if we bring the magnet away, the change in the magnetic field is going to be decreasing. The flux will be decreasing. And the magnetic field direction that a magnet produces with the South Pole pointing down would be vectors up. Okay. So in order to oppose this decreasing flux, we need a magnetic field to point in the same direction as the existing magnetic field. And that's the B induced that we do the right hand roll on. So thumb would be pointing up and then your fingers would be curling counterclockwise. And then finally, South Pole pointing down, velocity towards the coil. So the magnitude increases. Flux is increasing. To oppose the increasing flux, the induced magnetic field, it should point in the opposite direction as the B field. So then we put our thumb in the direction of B induced, and we see that our fingers are going clockwise. Okay? So that's applying Lenz's law. And there's many different, ways to do Lenz's law. So we saw that you can just have a B field vector, floating in space. You can have a magnet producing the magnetic field lines. Okay, and then another way is that you could have a current carrying wire producing magnetic fields. Just trying to do this in 3D. Like this, right? That's the magnetic field. Right? So we can change the flux by changing the magnetic field in several different ways. So this is Test Your Understanding. It's basically just an application of what we just did. All right, read through these concepts for Lenz's law. And so now let's go back to the slide wire generator. So we recently did a derivation for that. We saw this result. And the key word in this result is perpendicular. Okay. When a conducting rod moves perpendicular to a uniform field, there is a motional EMF induced. And what we saw in the derivation is that L, which is the length of the conductor, this L is this length right here, okay? And it's the length that is perpendicular to the velocity and also perpendicular to the field. And so this L here is a variable that if it changes, if it increases or decreases, that's going to affect the velocity, the voltage and the current flowing through that circuit. Okay, that's an important concept. So here we're just kind of plugging in some values. So suppose we have this rod and it's 0.10 meters long. So that'll be L. Okay, so suppose L is 0.1 meters, velocity 2.5 meters per second, resistance of the loop, and then the magnetic field. What is the motional EMF in the current? Don't worry about the force. We're not going to worry about that. Well, EMF, VBL, okay. Easy peasy. the key here, the most, the difficulty here is just knowing what's L, right? L is this length. That's L. So we plug in everything and then put it in the calculator. And then there's your answer for the voltage. And to find the current, well, V equals IR, right? So I should be E over R, and that's how you find the current. Easy stuff. What's not so straightforward is the induced electric fields. So here's Faraday's law again. Okay, this is Faraday's law. This is what we were just doing, except now we're representing epsilon, the EMF, in terms of an electric field. So remember from earlier in the course, we saw that a voltage can be found by integrating the electric field along the direction that you want to know the voltage. Okay, that's exactly what this is, right? This is simply a voltage. So this is just another way to write Faraday's law, a more general way. And this comes into play because you may have noticed that the voltages that we're calculating, right, they're not in a straight line, they're in a circle, right? The EMF is like a circular EMF. So it's not, you can't just multiply, E times some distance, delta X now. That distance is now a circumference of a circle. Okay, and that's simply what the left-hand side is telling you. So this statement of Faraday's law is saying that the electric field added up along every, infinitesimal portion of a circle is equal to the negative change in flux with respect to time. Okay, so the left-hand side is, if E is constant, just comes out to be E times 2 pi R, where R is the radius of the circle where you want to know the field, okay? And then the right-hand side is going to be the change in flux, okay? Where the area here is usually also the area of a circle, but it may not be the same circle where you know the field, right? This is the area of the conductor that is experiencing the flux. So this R that belongs to this area may not be the same R that you know or want to know the electric field on, okay? That's basically how you approach this. This is just another statement of Faraday's law, except we're expressing the voltage in terms of an electric field. So if this is weird to you, you may want to go back and look in chapter 24, and you'll see that we were doing an integral along a straight line. The only difference is now we're doing the integral in a circle, and that result ends up being just the circumference of the circle. Okay, so we don't need to worry about eddy currents or displacement currents. We're going to skip that. What I do want to talk about briefly, just for funsies, is Maxwell's equations. So we basically have been introduced to almost all of Maxwell's equations, 3 out of the 4. The fourth one, Ampere's law, we kind of skipped in the previous chapter. But I'll just briefly, I'll show you, I just want to show you the symmetry of it. So you're going to recall Gauss's law for electric field, right? E dot dA is equal to the charge enclosed over epsilon naught. We're all very, very, well-versed in that. And then we briefly talked about Gauss's law for B fields. And what we saw is that the integral of a B field contained in a surface, well, that's always going to equal 0. And so why is that? Why is one Gauss's law equal to some number, and why is another one equal to 0? So recall that charges, positive and negative charges, they are sources and sinks of electric fields, right? Negative charges produce electric fields that point directly towards the particle. Positive charges produce electric fields that point directly away. So if we were to enclose any of one of these, okay, on their own, if we were to enclose them, we would get a flux, right? Because there's no cancellation of these vectors. There's a flux here, we got to add them all up. Flux here, got to add them all up. So you're going to end up with a non-zero result unless of course you have equal but opposite signs in there, right? But now let's look at a magnet. So anything that produces a magnetic field is going to have a north and a south pole. Okay, why is my white not showing? There it is. And the magnetic field lines leave north and enter south, right? So you have essentially, for every single object that produces a magnetic field, it's a source and a sink. So if I were to enclose this guy, I would have all of my exiting vectors canceling off with all of my entering vectors. Okay, and so no matter what magnetic object I enclose in the surface, I will get a net zero flux because there will always be equal amount of vectors exiting the surface as entering the surface. So those are the two Gauss's laws that make up half of Maxwell's equations. The next two, one of them we just saw, Faraday's, right? And Faraday's law tells you that if we add up all the electric fields along a certain length, that's going to be equal to a change in magnetic flux with respect to time. So, and then finally the fourth one is if we add up all the magnetic fields in a certain length, well, that's going to be equal to the currents enclosed in that circle. Okay, so here you can kind of see the symmetry here. We got two area integrals, two line integrals, okay, and they alternate with basically what they're a function of, right? The left-hand side B, right-hand side deals with the electric field here, electric field on the left, magnetic field on the right, okay? So there's some beautiful symmetry here in this math. And these set of Maxwell's equations, they're going to come up again later on when we talk about electromagnetic waves and how they propagate, okay? So these are all general for if you're in a material or not. But we can make some, we can kind of like drop some terms off if we're in vacuum. So if we're in vacuum, there are no charges present, right? So there's going to be no Q's. And if we're in vacuum, there's no currents present, right? So there's going to be no I's. So in empty space, there's no conduction, currents, right? So there's no currents, there's no charges. We're alone in space. Okay? And so the symmetry is even more present when we're more visible when you're in a vacuum. Okay, you can see how completely symmetric and interesting and cool Maxwell's equations are. So we don't have any time to talk about this stuff. It's not going to be tested on, but if you are interested, you can certainly chat with me about it. I would be happy to talk about superconductors. Okay, so this ends part 2 of chapter 29.